All right, so now we're going to look at the mixture family of probability distributions. So in general, the mixture family is different from the exponential family, as you might expect. So a mixture family is in general different from an exponential family. But the family of discrete distributions Sn is both an exponential family and a mixture family. Okay, and then we're going to show that these families play a dual role, right? So these two families of probability distributions play a dual role, right? If you recall, the last time we had talked about this idea of the alternating projection method as a means of trying to find the divergence. It's like between two sets, right? And that's oftentimes referred to as the ENM, or the EM. It's like algorithm, and then the E, it's like corresponds to exponential, and M corresponds to the mixture family. And if you recall, it's like the alternating projection method. It's like projects with respect to sort of orthogonal projection, right? But with different notions of flatness, right? So you have both the primal, it's like orthogonal projection, as well as the dual orthogonal projection, and you keep alternating between the two. So if you recall that, it's like then you might have been primed, it's like to think of the fact that the exponential family and the mixture family are going to be dual in some way, shape, or form. Okay? Or there's some sort of duality relationship. So let's see where that's coming from. Okay? So if I'm given n plus 1 probability distributions, let's call them q0 of x all the way up to qn of x, which are linearly independent. Okay, you can compose a family of probability distributions, right? So we can compose a family of probability distributions which are given by the following. Okay. So what you're going to do essentially is that you're going to take a convex combination, it's like of these probability distributions, and by taking a convex combination, you guarantee that the resulting object you have is again a probability distribution in the sense that it satisfies a normalization condition. Okay. All right. So P of x eta is equal to the sum from I equals to 0 to n of eta I qi of x, where eta satisfies the a normalization condition. And eta I is positive. Okay. So this is what is called a mixture family. This is a statistical model called a mixture family. Okay, where your etas, as you might expect, is a coordinate system. Actually, you don't need all n plus 1. You only need n equals 1 to n. Sorry, eta 1 to eta n, right? If you recall. And then eta 0 is just obtained by the normalization condition, right? Which is the sum, what's 1 minus the sum of the other etas. 1 minus the sum from I equals 1 to n of eta I. Yeah, so sometimes you consider the closure of this family, it's like where instead of just being positive, it's like you allow the swing to be non-negative, right? All right, so anyway. So it's clear that this is, so if you consider this to be a mixture family, right, then it's clear that the discrete distributions are an example of a mixture family. We already saw that discrete distributions are a member of the exponential family, but it's also a member of the mixture family where the probability distributions being mixed are just the Kronecker delta product functions, right? So clearly, the discrete distributions are a mixture family. Right, as well as an exponential family. Okay. Right, and if it's not obvious, the eta i's are the pi's, right, and then the qi's of x are just delta I of x. And I goes from 0 to n. Okay. So the etas are a dual affine coordinate system for the exponential family of discrete distributions. We saw that before, in a sense, right? Yeah, before we use a different coordinate system, it's like, but we could just have easily use the pi's. Before we had log of pi divided by p0, right? But it's clear that there's a one-to-one correspondence. It's like between that coordinate system and second just the pi's as the coordinates. Okay. So now let's consider a general mixture family. So Now, consider a general mixture family. Which is not an exponential family. Okay. So, in that situation, it turns out that the negative entropy is still a convex function on this coordinate system. Okay. So even in this case, even then, the negative entropy which psi of eta, which is the integral of p x eta log of p x eta dx is a convex function of psi, of eta. Okay. So I can consider it as a dual convex function and I introduce a dual to this manifold of property distributions. Where eta is the dual affine coordinate system. All right. So the fact that you're starting with the dual affine coordinate system is not a problem, right? Because you have this convex function. You can take the Legendre transform of it to get the primal inside coordinate systems, and you can take the convex dual inside of this convex function to give you the primal convex function, if you will, right? Okay, so let's see what happens when you do that. So the primal affine coordinates, right, are obtained by Legendre transform with respect to this convex function, right? Primal affine coordinates are, let's call it theta, which is the gradient of this negative entropy, evaluated on the dual affine coordinate system, right? Eta. So this isn't a natural parameter. It's like of an exponential family, except for the case of discrete distributions, right? So this defines a primal affine structure. But this theta is not the natural parameter of an exponential family. Except for the case of discrete distributions. Okay, and then it's as we've mentioned before, right? When you have a convex function, which is the negative entropy, and you look at the associated Bregman divergence, then you get the KL divergence, and so this is true also here. So the divergence, sort of Bregman divergence, if you will, given by the negative entropy psi eta is the KL divergence. Okay. So this is equal to the integral of the probability log of the probability distribution divided by log of the other probability distribution. Okay, all right. So this is, this is how everything sort of fits together, right? All right. So anyway, so if you start with the mixture family, it's like you can introduce this dual affine coordinate system, right? And again, it's like you can look at the associated negative entropy. It's like as a dual convex function that induces a divergence function via this Bregman divergence construction. And via Legendre transform, you can construct then the associated primal coordinate system, primal affine coordinates. All right, and again, the problem, well, not a problem, but in general, right, these primal affine coordinates are not the natural parameters of an exponential family, right, except in the case where you have the discrete distributions. Okay, so let me just stop here for now.